Hi, everyone. Welcome to the last session of the day. So thank you for sticking around for this long, and excited to have a bunch of speakers to round this out. Just as a kind of, for both audience and the speakers, the way this is going to work is everybody has exactly 3 minutes. I'm going to give a verbal at 1 minute, a verbal warning, and then also when there's time, and there's a bell as well. So. I'm excited to introduce Sarit from Northwestern, who will be doing, from Kellogg, who will be doing the first lightning talk.
Okay, well, thank you. This is a fun paper about who gets and how much in the PBS vertical chain. And we all know here how it works. We basically have the it is working. So we basically have the users that are competing over getting their transactions into the builder's block. And we have the builders that are competing over having the proposers choose their blocks. And then we have the relays that are going to be also competing to make sure that the proposers are going to choose their blocks, right? So we have 4 different layers, and 3 of them are very, very competitive. So very intensive competition in the users market, in the builders market, in the relays market, and then we have a monopolist. Right? So if you're thinking about kind of like Econ 101, Econ 101 will tell us, hey, the monopolist should be getting all of the value in these transactions, right? So is that what we actually see in the data? The answer is no. So before I show you what we see in the data, I'm going to start with some definitions. So we have the block MEV value, and the block MEV value is going to be just the total block rewards. So these are going to be all the different transaction fees and priority fees minus the burn fees. Then we have the block value for the proposer. And then we have the percentage MEV. The percentage MEV is going to be the share that the proposers are able to capture out of the entire MEV value in the block. So taking as an example Lido, we collected data from early April to early May. We have about 181,000 blocks. And if you look at the data, what you see is that Lido is actually losing 24% of the block MEV value. So Lido is capturing only 76% of it, and that means that they're losing. They lost during our data time. They lost 1,666 ETH, and that pretty much, if you do a back of the envelope calculations, it's about 5% of their overall rewards during that time. Very, very large amount. So what is happening? Well, it turns out that it really, really varies. So this is not symmetric. What they're losing, the loss is not symmetric across builders and across blocks. So if you're looking at builders, then we have builders like Flashbot that give everything to the proposers, and then we have builders like Titan, Beaver, and rsync that are not doing that. But what's more interesting is that if we're looking at blocks with high banana gun primes, then you see that, for example, Titan, from subsidizing a lot of its blocks, they are now making money. So that tells us that there is something going on. We study what is going on, and we find that it has to do with exclusive relationships between the large transaction originators like Banana Gun and time's up. And block builders, and we study that and offer some solutions for the validators to get their monopolistic power back.
Thank you. Next up, we have Nikete, and we can do one question while we do the transition.
Okay, hello, I'm Nikete, Nicolas de la Pena, and we run a marketplace for LLM agents, and this is going to be a very, very brief talk about some ongoing work. I'm trying to basically a programmatic talk, so I'm trying to motivate you to think about LLMs for mechanism design, potentially for DeFi applications, and what's the right way of thinking about them. So mechanisms that rely on monetary reports, this is a very narrow information channel. So they fail in many cases to aggregate information. because when you observe your signal, you don't update your prior because you're not observing the other signals that are complementary that would be needed to unlock your prior. So there's a famous cases for prediction markets not aggregating information on this, but it's a much more general problem. So there's recently been some very exciting work on self-resolving mechanisms. So these are basically things that look a bit like a prediction market, but instead of, they don't need to look at the world. They instead of scoring you based on how your reports reflected in the real world, they score you based on how your reports are reflected in a reference agent that trades after you. So this same self-principle of self-resolution, we believe can be applied to these LLM-based mechanisms, because what matters about these reference agents is that they come after you. It means they have more information than you, so they're likely to be pointing in the direction of the truth, so that gives you an incentive to point in the direction of the truth. So to the extent that the LLMs have good world models and they can understand the value of the output that they're able to do given the signals that they've received, then we can use an LLM that has access to a wider set of signals, maybe sequentially because they arrive later, or maybe because we are synthetically like depriving the LLM of your signals or some other signals to create this reference. And we can use this to score you and create mechanisms where your reports, your signals are not trades, but are actually like natural language versions of your signals, and whether what the mechanism is doing is also itself effectively like a prompt to the LLM. And yeah, we're very excited, and this is very ongoing work. So this was mostly to encourage you to work in this area and collaborate. And if you have any questions, I can take them probably offline. Thank you so much.
Thank you. And have time for one question while Corinne comes up.
Can you hear me? Okay, great. Hi, everyone. I'm Corinne. I run a hedge fund that operates completely on chain. We do some liquidity provisioning, and today I'm going to be talking about some of our work on UV3. We focus on UV3 because you can concentrate liquidity, and the most concentrated liquidity range we're going to call a tick. This is an example of Uniswap.info last night. We're looking at ETH-USDC liquidity by tick, where the pink tick is the current price. And we're going to be solving how to provision liquidity on a tick-by-tick basis, assuming that we're going to hold that liquidity for a fixed time period T. So in this problem, there are 4 parameters that we're going to discuss. 2 of them are known. We can get the current liquidity by tick from Uniswap directly. This, we're going to call it B, and it is a vector. And the liquidity provider can also decide how much capital they want to provision across all the ticks. That's D, and it's a number. So the other 2 parameters are much more difficult to estimate. In fact, ultimately, we're going to say that the performance of the returns are going to depend on how well these parameters are estimated. But what we're going to do is we're going to separate out swap volume from price volatility. So by looking at swap volume, we're going to estimate what the expected revenue from fees will be on a tick-by-tick basis. And by separating out price volatility, we're going to look at what we expect the depreciation of reserves to be on a tick-by-tick basis. So ultimately, the optimization problem will be going back and forth between trying to maximize the fees on one side, but also minimizing the depreciation of reserves on the other. So you might notice that the figure on the right has a funny cusp-looking shape. This is how we calculate it. We come up with an estimate of the distribution of where we expect the price to be after period T. And we imagine that we're going to put 1 unit of capital across in each tick. Then this cusp-looking shape is the expected value of those reserves after time period T. So here's the optimization problem. The objective is a combination of the fees generated from the rewards, and we also look at the total value of the reserves, much of which is we expect to depreciate. The constraints here can be adjusted. For instance, we don't have to allocate all D capital reserves, so we can make it less than or equal to D. We can add constraints about related to risk or minimal expected returns. But the variable we're solving for here is a vector where the ith element is how much liquidity to provision to tick I. So this is a convex problem, which means that we can use CVXPy to solve for this very, very easily. In fact, I think it's, 8 lines of code, 12 lines of code. And here's a look at some of the qualitative results that we get. So the gray messages, the gray here are the current liquidity by tick. The green is what our model is telling us is the optimal. And as you can see, when you add more capital, there's this kind of bimodal shape that almost looks like a limit order book. Thank you.
Thank you very much, Corinne.
Happy to talk more offline, too.
Sorry, we're going fast. And next up, we have alignment games.
Hey everyone, I'm Alex, co-founder of Butter. We are working towards governance automation, or real DAOs. And I'm going to present to you alignment games, which is a class of mechanisms which aim at producing a measure of alignment within participants in a network, what some others call intersubjective truths. And I'm going to present a version which is about reward allocation, so you can think about rewards towards LPs or DAO contributors, etc. So here I've represented users on the left, and by the way, this is I'm using the syntax of compositional game theory, which I think is cool. So users, they produce contributions or any action. And then you have a set of aligners who are basically users who have put up a stake, and which are going to feed back into users an alignment measure, which you can think of as a reward. So we can expect under some conditions that this produces norms within the network, so which is hinted at by evolutionary game theory. And then the question is, how are aligners themselves producing something which is aligned? For that, we have reviewers on the right, and reviewers are going to feed back incentives into aligners. So you can think of it as 1% of what aligners do is reviewed by reviewers. Reviewers is a smaller set, they have higher stakes. And this way, aligners are playing a kind of prediction game where they are trying to predict how aligners are going to judge their work. Then, of course, last question, how are reviewers themselves aligned? And so for that, we can use a simple Schelling coin kind of mechanism or Keynesian beauty contest, which is a conforming mechanism where the majority is always winning. Yeah, so basically that's it for the quick overview. We are working on that because we think alignment is a key ingredient to making resilient and efficient protocols. That's it. Thanks for listening.
Thank you. And next we have Guy presenting on pro rata games.
Thank you. So as you can tell, these slides are quite fresh off the farm. Like they still have a little bit of dirt on them. But anyways, yeah, so this is Concave pro rata games, which is a weird paper that we wrote a little bit ago, which might be interesting given the whole discussion around batch auctions. So really quickly, what is a concave pro rata game? You have a bunch of players. They all put money into a pool. Then that pool essentially gets transferred to some function. We're going to call it F, right? And then into kind of F of P. So P is the total that everyone's put into the pool. You get F of P out, and then that output is split in a pro rata share amongst the original players. So if top player put in 1/5 of all of the value of the pool, then they get out 1/5 of F of P. Okay, and we say it's concave, of course, if the function F is concave. So one example of this is like a traditional batched exchange, such as Penumbra, which is if F is a CFMM's forward exchange function, like a natural question to ask about a market is, what does arbitrage on these markets look like? In other words, if everybody's an arbitrageur and like everyone's trying to kind of like match the price with an external one, right? Given like some external market that's infinitely liquid, what does arbitrage look like? What is this game that we set up? Of course, this is a game because you have responses to other players, etc. And so here's a fun fact. First, if f is a forward exchange function from a CFMM, f is concave, period. Number two, it is a nice model of like a batch auction that you might want to do if you want to like preserve privacy or things like that. And here are three fun properties that actually I don't know any real other game that satisfies this, which is one, it has a symmetric equilibrium for the arbitrage game. Number two, this equilibrium is easily computable, and I have no idea how to interpret actually the like solution at all whatsoever. So if anyone has any ideas, please let me know. And number three, it's actually unique. And fun fact, a standard result says something like the Rosen condition says, okay, if you have the Rosen condition, you satisfy these three things. That's kind of like the tightest result we know. It turns out that this game does not satisfy the Rosen condition at all, but it does model a bunch of interesting
1 minute.
programs. So with that, I just want to say thank you. And actually, that was a good 2 minute, and we're saving time. Thanks.
Awesome, thank you. And Ari is up next.
Oh, wow. All right.
App slides. I don't think so. No, sorry, not that prepared.
Yeah, no worries.
All right, 3 minutes. Go
Okay,
ahead.
great. Hey, everybody. I'm Ari from Arrakis Finance. You might know me as Cassandra.eth, Reverend Mother, online. And yeah, I want to tell you about the new product that we've built in collaboration with Volantis Labs. We'll hear more from them later in these lightning talks. But even before getting into it, since we only have 3 minutes, what I really want to tell you about is the motivation for this product. Essentially, as many of you have probably heard over the last couple of days and seen on chain, intense-based order flow for spot trading has grown immensely. And with the growth of intense-based order flow, you've also seen the growth of private market makers filling most of the flow on chain. So this means like people with their own assets simply giving quotes off chain, and just the fulfillment happens on chain. So our goal at Arrakis is to help make LPing, like on-chain trading experience much better for everyone, and allow for the long tail of participants to participate in liquidity providing. And we see a threat in the current market structure to this. And so our design response was to create a hybrid AMM design. We call it the HOT AMM for hybrid order types. And we love the AMM acronyms, so keep them coming. And the idea here is that there are actually 2 order types simultaneously in this one liquidity pool smart contract. So it's a hybrid design where you still have your sort of classical permissionless swaps that anybody can do. You can encode a swap the same way you might on Uniswap. However, you have a second order type, sort of a side door into the AMM. And this order type is just RFQ style quotes. So there is a quoting service run by Arrakis, which could be decentralized in interesting ways in the future. But at first, you can imagine the only checks on this are some sort of on-chain third-party oracle. And these off-chain signed quotes can execute directly against the pool reserves. However, there's some metadata in these off-chain signed quotes that also sort of refreshes the AMM. So it might magically jump the spot price to a new spot price, which comes from this metadata. And also every time one of these new off-chain quotes lands on chain against the AMM reserves, the swap fees for normal permissionless swappers will go down and then slowly increase over time until we observe another one of these quotes, which also acts as an oracle for the AMM. So the idea is help third-party LPs compete for this intense-based order flow and use the intense-based order flow to actually make the permissionless AMM more performant and have better spreads. So thanks so much. Please read the paper. Go to Arrakis Finance Twitter to see the paper and the blog about it. Thanks, everybody.
Awesome, thank you. And Devin up next.
Sweet. No slides. I'm going to use a bit of my 3 minutes just to say, like, I've been working on this for the past 2 years, never spoken about it publicly. I'm really excited. Couldn't imagine a better room to do this in. So Volantis is a protocol for building DEX protocols. And the reason I didn't just call us a DEX is because you could actually use this framework to recover any existing DEX protocol that you know today. You could recover a singleton hook-based architecture, really anything else you've seen. And the way that we do this is kind of stepping back and thinking about what are the design decisions that you need to make when building a decentralized exchange. And it's more than just pricing logic. It's pricing logic. Do you want RFQs, AMMs, order book style? But also, like, how is liquidity represented? How is it stored? How does it flow across pools or potentially other DeFi protocols? So the way that we did this is we constructed a core liquidity pool that is supposed to be the most generalized version of a DEX that we can think of. And it defines these role-specific modules. There's about 7 or 8 of them, and we think that this is the taxonomy of a DEX. For example, one of these, the only mandatory module, is the pricing module, and this will actually either host AMM logic, order book logic, something more interesting like hot AMM, which has the hybrid order type. And then you have other modules that deal with like data accumulators for like oracles, or how liquidity is stored, so you can recover singleton contracts, or you can potentially share liquidity across multiple pools. And the idea is that by it enforce some core invariance inside of the core liquidity pools. And the idea is that you can mediate the conversation between these modules in a way that allows you to basically add new modules into a pool while preserving a lot of the security properties that you get. And really kind of the thesis around this is that a lot of DeFi protocols that are built today are done in a way where they make very opinionated statements, where building new things can often warrant building from the empty address. People should never have to do this, in our opinion. So we kind of preserve a lot of properties around the reusability of code, and kind of the idea is that we will be, we think that you can build basically microcosms of DEX ecosystems, very similar to like kind of a Cosmos thesis, where each individual liquidity pool can make very custom statements about saying, hey, I trust the logic of these 3 pools, therefore I want to have my liquidity stored in a way where it can be deployed permissionlessly across these pools. And the idea of just creating a generalization of a DEX architecture is that you can build new protocols on top of it without ever starting from zero. And yeah, over time, as these modules get built out, they could be ported across pools very easily. Pools can integrate with shared sources of liquidity, shared sources of swap logic. And yeah, so we're building some cool stuff on top of it, doing some stuff around LVR and segmentation of order flow with Arrakis, also thinking about ETH derivative pricing. Yeah, I'll go ahead and stop here. Thanks so much.
Thank you. And Robert is up next.
Thanks, Theo.
3 minutes.
Awesome. I might even actually do this in under 3 minutes, because normally I would project some sort of white paper up there or something like that. But the last couple of years, I would say about 2 years, I've been working on this thing called a replicating market maker, which was inspired by Gilly's paper over there. And effectively, the idea is invariance for AMMs can essentially be used to get any sort of payoff to the person that's providing liquidity. What's really interesting about this is that if you actually invert the LP share of an AMM, so let's say like Uniswap, you get this really cool property, which is leverage. And so one of the things that we've been exploring over the past 2 years is, can we change that invariance so that we get a very specific type of options payoff? And so there's this really cool thing in crypto, which is a power perpetual instrument. What it effectively tries to do is condense an options exposure into a perpetual type of contract. So you can imagine, options are really good for getting asymmetric exposure. Perpetual futures today only give you linear exposure, which is kind of crappy. And what if we could package that into an AMM style system where it can be Oracle free and you can bootstrap a market with the simplicity of an AMM and also market on pretty much any token. And so there's some really cool future theoretical work that can be done in terms of optimizing this kind of payoff and also optimizing the funding that is required to maintain the convexity. I'll kind of leave it at that, but the TLDR is, finance works and functions as a system to share and transfer risk between folks. And I think if the space moves forward beyond just speculating on crypto assets, there has to be a way to transfer risk more efficiently, and options are the building block for doing this. So I really think folks should be focusing more on trying to build option products and trying to build better systems for transferring risk. And I think AMMs and specifically replicating options with AMMs is a really fantastic way to do this. That's it.
Thank you. You can put that up there. Next up, we have Ludwig from Sorella. We're 3 minutes.
Hi, everyone. So this is just a real quick introduction to an open source project that we've been working on for a while now called Brontes. And so basically the essence of why we built this is that, as you've all seen, we're all quite interested in MEV, and tracing and actually detecting it systematically is quite complex. There haven't really been open source repositories and tools that enable you to identify this like more complex activity on chain. And so what we kind of decided to build is an underlying analysis pipeline that enables you to very simply implement your custom inspectors so you can identify this complex activity. And so the TLDR there on how it essentially works is that the most annoying step for all of your work in terms of research when you're looking at empirical data is that it's extremely poorly formatted. You don't really have easily normalized and accessible data sources on DeFi because all of these various protocols have these slightly different implementations of a swap and the same underlying primitives. So we implemented a block tracing system that will systematically decode and normalize across the board, where you can very easily implement protocol classifiers that will render and return a single unified type. And so how that process works, I'll probably glimpse over this, but in essence, at the trace level, you're able to announce and implement a classifier for Uniswap, a classifier for Curve, or whatever other DeFi primitive or protocol that you're interested in, and you will get the normalized action returned to you at each step and very effectively. And the other problem that comes up in classification and analysis is that we don't really have access to the off-chain data that is necessary for this analysis, particularly
1 minute.
when you're interested in SexDex. And so what we did there is we collected and are open sourcing a repository of all of the primary centralized exchange pricing data and also significant address metadata. And so in the end of this, what you as a researcher or developer or data analyst can do is that you can implement an inspector. And that inspector can kind of look at any on-chain activity with the data and the pre-processing done for you. So you take in a block tree, which is effectively like the sequence of transaction traces that are classified and normalized into single actions. And on top of that, the metadata, which contains centralized exchange pricing, mempool data, whatever you'd really need to do that analysis. And then you can do any custom logic to be able and identify like various forms of strategies. I'll probably glimpse over this because we do not have
10
time.
seconds.
But what you have already today is that we're opening up an API where you have access to 95 to 99% of the JIT sandwiches, SexDex, sandwich attacks, atomic arbitrages, and in general, just searcher transactions that have been detected. And in the future, what you can implement is you can—
And that's time. So, thank you, sorry.
Right.
But please find all the speakers afterwards. Kshitij is up next. You have slides, right? Yeah. All right,
Do I?
3 minutes.
All right. Hi, everyone. Today I'm going to be talking about these protocols that are systems that are coming up called intent protocols. And this talk is almost an IRL shitpost, but yeah, feel free to read the paper at the end of the day. All right. So yeah, intents is the new buzzword on the block. We have lots of news articles, investments, and protocols coming up. So the question is, what are intents? In theory, they allow users to express preferences about things that they want, and these entities called solvers will fill their orders. So for example, A user says, I want to buy 1 ETH at the cheapest available price and then only fill my order if the price is less than some amount. And then on the other side, you have these entities called solvers. Their names might even be Sarah CP and William M. And we have this nice tweet that says, if you have bidders in crypto papers, you should call them Sarah and William for a reason. In practice, these things look a lot like rebranded RFQ systems, but naming things differently is great for sites, grants, and VC funding. So is the hype warranted? Some people are skeptical. You have these tweets, intents fix this, assuming there's an omnipotent, computationally unbounded agent willing to fill my intent for 1 cent of profit. I don't know such people, but you might. This is for good reason that people are skeptical because these markets tend to result in oligopoly and concentration. And if you don't want to know why, read this paper. Okay.
Great, thank you. And next we have Naveen.
Hey guys, I'm Naveen. I'm a PhD student at Columbia with Tim Roughgarden. I'm sure many of you have heard about EigenLayer recently. The security of restaking networks is something I've been thinking about a lot in the last several months. And yeah, as we know, Ethereum is secured by proof of stake. One way to depict that is that you could imagine Ethereum's on the left here. There's some validators that each have some stake, and that stake is what's securing Ethereum. The main premise of restaking is kind of when can you actually reuse some of these validators. So for example, another service might come up and you might want to reuse the stake that these two validators have. And why might you want to do that? The main idea is that the stake has already locked capital. So from the perspective of this service, they don't need to compensate these validators for the cost of capital because it's already locked into Ethereum. And from the perspective of these validators, they're getting additional yield in exchange for validating for this service. So this all sounds great, but also seems like it makes things less secure. What I worked on is understanding under what circumstances can you actually do this in a way that might be considered safe. We might think of Ethereum as safe if the total stake, the 1/3 of the total stake is greater than the cost of corrupting Ethereum. In the general case, when you have an arbitrary bipartite graph here, for things to be safe, it must be the case that the total stake for any coalition of validators that can corrupt some subset of services must be greater than the profit from corrupting all of those services. And so this is already kind of a more complicated model to work in. But I'd agree that that type of security is also not even sufficient because things are also bad. If a small shock to the stake supply leads to a catastrophic worst-case scenario where many people start attacking series of services in a cascade. And so what I look at is in a pretty general attack model, what are conditions to prevent that from occurring? The main result is that essentially specific forms of over-collateralization are both necessary and sufficient to prevent worst-case, or at least mitigate worst-case outcomes. So yeah, that's about it. If you think that's interesting, the full paper that includes far more technical details will be out in the next week or so, hopefully. So yeah, thanks.
Thank you, Naveen. And Ethan is the last one to round out the lightning talk session.
All right, my name is Ethan, founder of Allium. So just want to talk about the Uniswap Foundation grant that we received from Uniswap Foundation. So our goal is just to make your lives easier. As researchers, we just, at Allium, all we do is just handle your data needs. So we have DEX trades, DeFi trades, liquidity pools, all that. We already onboarded about 10 researchers in the past month, including Austin Adams' V3 Polars project. You can connect the data through there. Also Tivas from Consensus. Yeah, so TLDR, if you have any data needs, just contact me. So maybe I'll write my email here until we get a website, right? This is paid for by the Uniswap Foundation, so just come here. This is the no slides, so just email me for now. If you need any data help, just ping me and we'll do our best to help you guys with all your DeFi data needs. So with that, thank you. Yeah.
Awesome, thank you. And can we give everybody that did a lightning talk another round of applause?